This video is a brief introduction to a project funded by the National Science Foundation Cyber-Physical Systems Program, entitled Analysis, Identification, and Mitigation of Delay Performance Bottlenecks of Network Infrastructure in Cyber-Physical Systems. It is funded by the NSF and the principal investigator is Professor Liang Cheng. This project focuses on Ethernet for cyber-physical systems, abbreviated as CPS. CPS are engineered systems that are built from, and depend upon, the seamless integration of computation and physical components. Network technologies such as Ethernet are used to connect different components of CPS, and they are widely applied to industrial control systems, avionics systems, and vehicular networks. With the development of Industry 4.0 and 5G, more controllers, sensors, and actuators will access and use traditional communication networks. As network traffic increases, so do end-to-end communication delays. However, certain critical applications require a guaranteed maximum end-to-end delay. To guarantee the latency performance of these critical data flows, we implement deterministic performance analysis of cyber-physical systems with random processes. The aim of our project is to establish a systematic approach to design, characterize, and refine the network infrastructure in CPS to meet the latency requirements of time-critical flows. We use network calculus as the theoretical framework for this project because it is designed to provide deterministic performance guarantees in computer networks. We aim to develop both software and hardware for the outer research groups. An additional aim of the project is to develop a method to analyze non-feed-forward networks, in contrast to state-of-the-art network calculus methods that target feed-forward networks. Non-feed-forward networks are networks that have bidirectional or cyclic communication. An example of this is a centralized controller using multiple feedback control loops over a network. First, we introduce network calculus. To use network calculus, we should characterize the flows and switches. A switch is networking hardware that connects devices on a computer network. Flows and switches are described with arrival curves and service curves, respectively. An arrival curve is the upper bound of the cumulative curve of data packets arriving to a switch. The service curve is the minimum performance which is guaranteed by the switch. In Figure 1, S is a switch. Alpha T and alpha prime T are the arrival curves of the incoming traffic and the outgoing traffic, respectively. Beta T is the service curve of S. To conduct a deterministic latency analysis, we need the two curves alpha T and beta T. In Figure 2, the red line is the arrival curve and the blue line is the service curve. The maximum end-to-end delay is the maximal horizontal gap between the curves, which is H alpha beta. Next, we will introduce the topology of the test bed. In this experiment, we use a 4-node tandem network topology which is shown in the figure and photo. Flow F1, which is from sender 1 to the receiver, is the flow that we are interested in. The network topology is flexible and inexpensive, using Raspberry Pis that can connect to up to 5 other devices. In the photo, cables are connected if they have the same color label. The Ethernet port with the orange label is connected to the receiver, and the black cable with the blue label is connected to the sender 1. This testbed allows us to create arrival curves for the data flows and service curves for the switches. Then, we can feed these curves into a network calculus analysis to get the analytical maximum end-to-end delay bounds for the data flows. The analytical delay results are compared against the empirical testbed delay results. The analytical results should upper bound the empirical results. Last, we can calculate the maximum bound of end-to-end delay based on the arrival and service curves modeled by the test bed. We use a network calculus toolbox called DiscoDNC to do the calculation. It shows the resulting upper bound, which is approximately 0.37 seconds. The empirical measurement is 0.174 seconds, which is well below the upper bound. This comparison shows a limitation of the network calculus, which is the tightness of the bound. Since network calculus takes the upper bound of input traffic and the lower bound of the guaranteed service, the discrepancy between the analytical bound and the measurement result might be large. We want to find the reason causing the discrepancy and minimize it to make the bound tighter. If you are interested in our project, please contact Professor Liang Cheng.